Good morning students. Beta, in our today's class I am going to discuss with you the diffraction pattern which we get when we did the diffraction due to single slit. Even that time I draw the curve, but I forgot to discuss that curve. So in today's class we'll do that curve. Okay beta. Now let's start. Beta, the pattern which we get on the screen due to, okay, it's clear now. Okay, the pattern which we get on the screen due to the superposition of the waves emitting from the part A and B of the slit is like this. At the central point of the screen we get the maxima, and on the both side of this maxima we get the points of minima and the maximum intensity, and we name them as the first secondary maxima, second secondary maxima, third, and so on. And for the minimum we call them as the first secondary minima, second secondary minima, and so on. See beta. Beta, I draw the curve between the intensity and the path difference that time. You can also explain it by taking the parameters as the intensity and the diffraction angle. We can explain it both the ways. Beta, these are the points of the, these dip are the points of the minimum intensity, and these peaks are the points of the maximum intensity. So this is my first minimum point or first minimum intensity point on the either side of this maximum intensity point. So we call this point as the first secondary minima, and this is the point of the second secondary minima. We get this minimum intensity point on the both sides of the central maxima, and we find out the conditions that we get this maxima and the minimum intensity. It all depends upon the path difference between the waves which are originating from the portion AB of the screen, and we calculated the conditions there. For the minima, the path difference is lambda, minus lambda, 2 lambda, minus 2 lambda, 3 lambda, minus 3 lambda, and so on. And the beta, these peaks we get on the both sides, these are of maximum intensity, and we call the first peak we get on the both side of this maximum intensity peak, we call it as the first secondary maxima. This we'll discuss in today's class, their intensity. This is our second secondary maxima, and this is our third, and so on. But you can clearly see in the figure that the intensity of the central maxima, this maximum point, this is called our central maxima, that the intensity of the central maxima is the highest, and then the intensity of the, this is my first secondary minima, is less than that of the central maxima, and the second secondary maxima intensity is less than that of the first and the central maxima. Why the intensity goes on decreasing? See what happened beta. We'll get the maximum intensity at point O. We get, this is our point O. We get at point O the maximum intensity, because the rays which are falling on the portion AB of the slit, they meet at point O on the screen after covering the same distance. That's why their path difference is 0, and at point O we get the maximum intensity, and this maximum intensity we called as the central maxima. And you remember that time I consider a point P at some distance from the central point O, and that point P we calculated can be of maximum intensity or of minimum intensity. Everything depends upon the path difference between the rays which are emitting from after diffraction, from after when the light strike on this portion AB of the slit, the rays get diffracted, and after diffraction they meet at point O. It depends upon their path difference. If they're and we already calculated the conditions of the path difference when we get the maximum intensity point at P, when we get the minimum intensity at point P. See beta, the point P is always of maximum intensity in comparison to this other maximum points. Why is it so? Because the light which falls on the portion AB of the slit, here the whole of the light is falling on this portion AB and whole of the light is converging at point O on the screen. That's why point O is of maximum intensity. Is it clear? Now let's see why the intensity of first secondary maxima is less than that of the central, and so the second, and so on. Beta, you remember that the we get maxima at point P when the path difference between the waves originating from portion AB of the slit is odd multiple of lambda by 2. Here n starts from 1, 2 and so on. So we get the first secondary maxima. For first secondary maxima we put n is equal to 1 here. So for the first secondary maxima, when I put n1 here, we get the 3 lambda by 2. We get the first secondary maxima when the path difference is odd multiple of lambda by 2, or path difference between the waves originating from portion A and B of the screen is 3 lambda by 2. And beta, that time I already told you when the path difference is 3 lambda by 2, that time our slit AB is divided into 3 equal halves, and the waves emitting from, I am dividing this 3 lambda by 2 into 3 equal halves. And now that time the waves emitting from these first and second half of the slit, the waves superimpose destructively, and at point P we do not get light. So at point P we get light only from the waves emitting from this third part of the slit. So we can say at point P of the screen we get light only due to this 1/3 part of the slit, because light is falling on the only 1/3 part of the slit which is superimposing constructively, and we get the bright spot on the point P. Now see beta, the light which we get at the central point, this most of the light is concentrated at the center. Why most of the light is concentrated at the center? Because at you can clearly see in this case the whole of the light is falling on the screen, not screen, this slit, the falling on the slit, and the whole light is converging at the slit, not slit screen. Okay beta, now see here, in this case only 1/3 part of the light falls, which is utilizing here is only 1/3 part of the light which is coming from this third portion of the slit. Now beta, see why the intensity of the same is the case with the intensity of the second secondary maxima. What happens that time? The path differences for second secondary maxima, when I put n2 here, the path difference comes out to be, we already discussed these things there, comes out to be 5 lambda by 2. Now that time I told you we divide the slit into 5 equal parts. When I divide the slit into 5 equal parts, then the light which reaches point P from the first 4 portion, the light superimposed destructively, and the light which reaches at point P, that is only from this 5th part of the slit. So we can say the light which reaches at point P is coming from only 1/5 part of the slit. That's why That's why the intensity of secondary maxima, second secondary maxima, is less than that of first and the central one, because the light which is reaching in the central one case, in the central maxima case, is coming from the whole portion of the slit. The light reaches on the screen is only due to the 1/3 part of the slit, and in the second secondary maxima the intensity of light is only due to the 1/5 part of the slit. So it's coming from the only 1/5 part of the slit. So the portion of the slit goes on decreasing. So the portion of the light which reaches, the part of the light which reaches at the screen, goes on decreasing. That's why the intensity of the maximas keep on decreasing on either side of this central maxima. This is the reason. And beta, you can clearly see the intensity curve which we get in this diffraction pattern is entirely different from that of the interference pattern. And one thing is left in this diffraction due to single slit, and that is our calculation of width of central maxima, which we will do in our next class. Thank you, beta.